We stare at glowing rectangles all day, trusting the glass and metal to instantly answer our questions. Yet, if you ask most people what is actually happening inside that case, you'll usually get a blank stare. We tend to anthropomorphize microchips. We think of them as tiny brains that somehow understand math or logic, but they don't know anything. They are just cold, physical objects channeling electricity. This diagram shows the absolute base unit of all computing, a single physical wire. It only has two possible states. Electricity is either flowing, giving us an active 1, or it isn't, giving us an inactive 0. If we start with just this one switch, we can strictly apply a few rules of logic, stack these switches piece by piece, and construct a fully functioning computer brain. You don't need to understand advanced calculus to see how this works. You only need to see how incredibly simple things, repeated enough times, build an illusion of massive complexity. Looking at this early experimental transistor, we see our first real hardware component. A transistor is just a microscopic gatekeeper. Apply a specific voltage to it, and it allows electrical current to flow through. Take a look at this schematic. By wiring two of these transistors together, we create an AND gate. It does exactly what it sounds like. The output line only lights up with a 1 if the first input and the second input are both turned on. Now, if we place a simpler circuit right next to it, called a NOT gate, its only job is to invert the incoming signal. A 0 becomes a 1, and a 1 becomes a 0. Combine an AND gate with a NOT gate, and you get a NAND gate. The output remains active unless both inputs are active. That specific arrangement is arguably the most critical invention in the history of computer science. It is a functionally universal atom. Every single logical operation a modern computer performs can be physically built using nothing but NAND gates. Humans count using a base 10 decimal system, 10 digits multiplied by powers of 10. Machines rely on a base 2 binary system, scaling numbers using only those 0 and 1 states multiplied by powers of 2. This diagram shows a half-adder circuit made of exactly 5 NAND gates. Watch as two input bits move through the gates. The circuit adds them together to output a 1 and a 0, which is binary for 2. It also calculates a carry bit to pass to the next column. Adding up to 2 isn't very helpful on its own, but if we daisy chain multiple adders together into a full adder, the circuit can accept that incoming carry value. Now the machine can add larger numbers, smoothly taking a binary 5 and a binary 4, and outputting a 9. To make that output readable for us, the computer sends the binary result through a decoder. This circuit simply illuminates specific physical segments on an LED display, perfectly translating the machine's binary math into a human-readable 9. By adding a few more gates to toggle a subtraction mode, we've upgraded our adder into an arithmetic logic unit, or ALU. It can now process negative numbers and complex equations. But an ALU alone is not a computer. It suffers from total amnesia. The moment the operation finishes, the answer is gone. It needs a physical way to remember. Here, we see a clever mechanical trick called a latch. By looping the output of a logic gate directly back into its own input, the signal continuously cycles. It permanently locks its state to on, saving the data. Stack an array of these latches together, and you've built a register. Think of it as a short-term memory slot where the ALU can fetch and store numbers while working. But numbers aren't the only thing the machine has to store. The actual programs, the long sequences of instructions telling the machine what to do next, must also live physically inside the hardware. Engineers solve this using the Harvard architecture model, a structural approach that strictly separates the system into two distinct memory banks, one dedicated to storing instructions and another for storing the math data. We now have memory to hold our data and a calculator to process it. The physical body of the computer is complete. All it lacks is a conductor to orchestrate the work. That final component is the control unit. Looking at the dense layout of these microchips, this hardware is engineered to automatically fetch instructions from memory, decode them, and route tasks directly to the ALU. But humans can't write instructions strictly in ones and zeros. Manually flipping bits for thousands of operations is an impossible bottleneck. To fix this, we use an assembler. This is a critical software translator that converts easy-to-read text commands typed by humans into the raw binary machine code the hardware demands. This enables the fetch-execute cycle. A simple line of text tells the control unit exactly which physical memory address holds the data and exactly where it needs to route it. Programming code isn't magic. It is simply a set of hyper-specific physical coordinates telling the control unit which microscopic switches to flip. When we run a program, like a Fibonacci sequence, the system comes alive. The CPU seamlessly fetches instructions, routes the data, adds the previous numbers together, and stores the result back in memory, over and over. Modern engineers layer dizzying enhancements on top of this basic model. They use pipelining, cache memory, and parallel processing to execute billions of cycles a second. Yet even when looking at the massive physical scale of this classic IBM computing room, the foundational architectural reality of the machine remains identical to our single switch. The ultimate power of technology is merely an illusion of scale. The screen you are looking at right now is strictly just billions of microscopic on and off switches, all working in perfect harmony.